today's speaker. Francisco did his bachelor's degree in math and physics at the University Complutense of Madrid. Then he finished his master's degree in math at the same university. He started his PhD in Qusoft in Amsterdam in 2021, and his research interests are the interplay of functional analysis with quantum information, quantum query complexity, and non-local games. And let's welcome Francisco.
Yeah, thank you very much for the kind introduction. Also, thank you very much for the invitation. I'm very happy to be here giving the seminar. First thing I want to say is that if you have any question during the talk, please don't hesitate to interrupt. It's better to understand than to go fast. Okay, so this work is a work generally done with my PhD supervisor, Gutiérrez, and is titled Converses to the Polynomial Method. This is on arXiv, was also published in the QC proceedings of this year. And the structure of this presentation is going to consist on 4 parts. In the first one, we are going to give an introduction to quantum query complexity and the polynomial method. Then we are going to state our results. And in the third part, what we're going to do is introduce the tool that we are going to use to sketch the proof. Finally, what we are going to do is sum everything up. And I speak about a forthcoming work that is going to be a continuation of this work that I'm going to present. And in this forthcoming work, which is going to be out probably next week, we are going to improve the results that we are going to present now. Okay, so let's go with the introduction. First of all, we have to speak about Boolean functions, which for us, they are just going to be functions defined on the Boolean hypercube that also take Boolean values. And here Boolean means -1, 1. Sorry if you like more the 0, 1 setting, but for us it's more interesting to work with the -1, 1 scenario. Okay, so it's very natural to compute this kind of functions with a classical computer because these are the naturally encoded functions with bits. What you can do with a classical computer, if you don't care about your resources, you can simply read x. If you want to compute f of x, you read the whole input x and then output f of x. But maybe that is not desirable because reading the whole input can be super expensive. So instead, what you try to do with a classical computer is reading some parts of the input and try to output something that is close to f of x with high probability. Okay, so this way, what we are going to define as our unit of computational effort in the classical world is looking at one of the entry of the input. And looking at one of the entry of the input is what we are going to call making a classical query, which is the same as applying this map, which is what we are going to call the Oracle X map that maps the numbers from 1 to the n to the corresponding entries of the input. So this map contains information about the input. So that is the classical setting. And now we can wonder which is a natural generalization to the quantum world. And we want to generalize things in the quantum world in a way such that is the analog way, but also we can use the power of quantum. In particular, we are going to try to use the power of quantum in the particular case of superposition. So now our oracle is going to be a map that is going to be a linear map. A gate is also going to be unitary that maps an n-dimensional Hilbert space to itself in a way such that you fix a basis and you map the ith element of the basis to the ith element of the basis times the ith entry of the input. This way, if we apply this gate, this oracle gate, to the maximally superposed state, we obtain all the information about the input in the position.
Hello?
So, okay, good. Sorry.
Hello, I have a question.
Yeah, sure.
Okay, so on the top, you see like little x is an n-bit string, and I is, so I didn't understand this particular equation, the first equation, OX of I is equal to XI. What does that mean again?
Okay, that is the axis. Our computational unit of effort is going to be using once this map. That is an oracle that maps the numbers from 1 to the n to the corresponding address of the input. So,
okay, so it gives component of the ith component of x.
yes. Yes. Sorry if that was not clear. So, in a classical algorithm, the way of accessing the input is using these oracle maps, and in the quantum setting is going to be using the quantum oracles.
Okay, and the function has not come in at this point, is it? Like the little f that has not come in at this point.
Okay, you assume that you know the little f, and you want to design an algorithm that the only way of accessing the input is through these oracles that outputs that f on every input with high probability.
Okay.
Okay, so
Thanks.
maybe that was. Is it clear now? Or
I think so.
okay, good. So the goal is knowing f, trying to design an algorithm that outputs f of x on every input with high probability, using accessing the input only through these kind of special gates, which are different in the classical case and in the quantum case. In the classical case, they are less powerful because in the quantum case, we can do at least the same if we work in the basis states, but we can do more because we can access all the input in all the input information if we apply the oracle gate to a maximally superposed state. So that is the setting, and that is why intuitively, this is not rigorous, but that is why intuitively is going to be easier to compute things with quantum computers than with classical computers. Okay? So
okay.
is it clear so far?
Yeah, I think so.
Okay, good. So now we are going to formally define what is a quantum algorithm, a quantum query algorithm. We are not going to talk about classical query algorithms. I just introduce what is a classical query informally in order to motivate the quantum setting. And a quantum query algorithm is going to be an algorithm defined in the following way. For every x of the domain, you design a quantum circuit in the following way. You alternate fixed unitaries with these oracle gates that we have introduced before that contain the information about the input. So for every x, you have a different circuit, and these circuits only differ on the use of this oracle x's gate that contain the information about the input, and thus they are different for every input. At the end of these circuits, you measure one qubit. And if you measure 0, you say that your output is going to be, the output of your measurement is going to be -1, and if you measure 1, the output of your measurement is going to be 1. So at the end of the day, for every x, you're going to have a random variable that is going to take values 1 and -1. So the expectation of that random variable is going to be lying between -1 and 1. It's going to be bounded. And this way, what we are going to have is, what our goal is going to be that such that for every x, we choose these unitaries that are fixed for all the x's. We want to choose these unitaries wisely in a way such that we obtain an expectation of every random variable defined by every x that is close to f of x. So we want to approximate f of x with the expectation of the random variable defined by this circuit plus measurement for every x. Okay, so we are going to say that this is a quantum query algorithm that does the queries if it uses t times this oracle gate. If you use more gates, you are going to have more power because you are going to have more access to the input informally. So now we are ready to define what is the quantum approximate query complexity. And given a positive number epsilon and a Boolean function f, the quantum epsilon query complexity of f is the minimum number of quantum queries that an algorithm have to make in order to approximate f in expectation, up to an error 2 epsilon. The 2 is there just for historical reason. So this is the quantity that one wants to compute to know how hard it is to compute a Boolean function using quantum query algorithms. Is it clear everything so far?
Sorry, I have a question.
Yes.
So in the circuit diagram you plot above, what's the x correspond to? They are correspond to different qubit. The x in the
yes.
in the. So the answer is yes.
Can you repeat, please? I couldn't hear it clearly.
You cannot hear me? Okay. I'm asking in the circuit what's the corresponding x? They are referring to different qubit, all the qubit in the queue. Is that the case?
No, I mean, we have as for every x is an element of the domain of the Boolean function. Okay.
Yeah, it's the domain. Yeah, I know.
Okay, and for every x, you are going to have a quantum circuit. And that quantum circuit is going to differ on this oracle X gate because this oracle X gate is different for every X.
Oh, it's a
So-
function and depth, so it's valid for every x. That's what I mean.
Yes, it does.
Then our purpose is to find to compute this fx for every input we put on Q.
Yes. And to do so, you have to choose wisely your fixed unitaries.
Or the U0 to UT.
Yes.
And OX is fixed.
What?
The OX in between U, are they fixed?
They are fixed. Yes, they vary with the x's, but those are always the same for every quantum query algorithm.
Okay, I
because
see.
that is the canonical way of accessing the input. That is your oracle model.
Okay, and then what's the A mapping here? Is
Okay, yeah, I don't want to talk about that, but I lied a bit, not a lot, but okay, the W register is simply extra qubits that you can use, and the A register is the qubit where you measure, and
So
the
it's-
Q.
so it's just referred to register for 1 qubit, or it can be larger.
Yes. The W is like extra ancillary registers that you might need to do some extra operation. And A and Q is where the oracle acts. And A is an important qubit somehow because it's where you measure. This is not exactly this, but I think that is going to be a bit more complicated if I enter into the details just by words. But essentially, they are simply different registers that have a few differences. But essentially, what we care about is that we are alternating fixed unitaries that we have to choose wisely with these unitaries that are special, the oracles that contain information about the input, and then we measure 1 qubit. It's not going to be super important to know which these registers mean.
Okay, I see. Thank you.
Okay, good. Then we finish this introduction to quantum query complexity, and now, oops. Sorry, the light goes off from time to time if I don't move. Okay, so now we have finished with the introduction to quantum query complexity, and now we can wonder about how are the outputs of these quantum query algorithms. And the first people wondering about how are the outputs of these quantum query algorithms were Beers, Burman, Cliff, Mosk, and De Wolf more than 20 years ago, where they proved the polynomial method. And the polynomial method says that if you have a quantum query algorithm that does T queries, then the output of that algorithm is going to be a polynomial that is going to be bounded in the sense that is going to take values between -1 and 1, as we have already argued, and is also going to be bounded by above in degree, by 2t. So this is interesting because it tells you that if you have a quantum query algorithm that does T queries, then the output of that quantum query algorithm is going to be something that you can somehow control and understand, which is a polynomial that is bounded and bounded in degree, depending on the number of queries. Okay, so now let's introduce another measurement of complexity. We have just introduced one measure of complexity, which was the quantum approximate query complexity, and now we are going to introduce another measure of complexity, which is the approximate degree. It's defined in the same way as the quantum approximate complexity, but now instead of approximating the function with quantum query algorithms, we are going to approximate the function with bounded polynomials of degree at most t. And with this definition, the previous definition, and this result by Bills and co-authors, we can relate the two measures of complexity that we have introduced so far. Okay, first of all, I want to stress that here the polynomial being bounded means that the infinity norm of the polynomial, which is defined as taking the maximum of the values of the polynomial in the elements of the polynomial cube, is at most 1. Saying that P is bounded is the same as saying that the infinity norm of the polynomial is going to be at most 1. We are going to need this to motivate a bit some of the things that we're going to say later. But now we come back to the fact that we have two measures of complexity that can be related to by the polynomial method, and this relation is the following: the approximate degree is a lower bound of 2 times the approximate quantum query complexity, and this is true because if you have a quantum query algorithm, then you have a polynomial that has at most 2 times the number of queries that the query algorithm did as a degree, and it's also bounded. So now, if we wanted to prove a lower bound on how difficult it is to compute something with a quantum computer, we can forget about the quantum, which can be unstructured, which can be a bit more complicated than what we can get now, which is trying to show a lower bound of how difficult it is to approximate the function using polynomials, which are objects that people have studied a lot, mathematicians have studied a lot, and we understand very well. So this is nice, because now we can forget about the quantum problem and just talk about something that we control, which are polynomials. But this is not only nice, it's also useful. This is not something, an idea that was an idea without an application, but it has an application. Already in the original paper of Bills and co-authors, they showed that Grover was optimal using this approach of lower bounding the quantum query complexity through the approximate degree. And to do so, they used this result, but they didn't prove something new, because Grover was known to be optimal before this result came out. But there were also new results proved using this polynomial method. For example, Aronson and C in 2004 proved that the collision finding and limiting distinctness algorithms that we know nowadays were optimal. So these are results, the polynomial method that is nice and also useful. So now what we can do as mathematicians is wondering about more philosophical questions, and in particular, if I see a theorem, I always wonder if the theorem has just one implication, is the other implication true? So does this theorem admit a converse? And in this case, this is not true. It's not true that you have the implication from the right to the left. In other words, there is no pure converse for the polynomial method. And this means that it's not true that for every bounded polynomial of degree at most 2t, there exists a t-query quantum algorithm that puts that polynomial in expectation. Okay, and this can be proved as a consequence of, for example, this can be seen in many ways, but for example, you can go to a work of Ambani's in 2004, and this is an easy consequence of his work. So this finishes the introduction. I hope that now what the polynomial method is clear for you, and if you have any question, I will be glad to answer.
Sorry, can you see the explain the bottom line again? You mean there is no right direction guarantee. So your purpose, do you want to say do something related to this, or this is just a fact?
Yes. Now this is just a fact that there is no pure converse of the polynomial method, but now, as there is no pure converse, we can wonder if there is another kind of converses. Maybe there are things that look like a converse, but they are not a pure converse. And that is what we are going to do next.
Oh, you're going to do this. Okay, I see. Thank you.
Yeah. In the next slide, we are going to talk about which can be a reasonable converse that is both true and not super far from being a mathematical converse to this result.
Okay.
Okay.
Could you explain a bit more about the A, like in the theorem you're showing here, like A does T queries?
Oh yeah,
and
sorry.
What is this A of X? Like, if what's the output of this?
Okay, good. Thank you for the question. Maybe I was not clear. A is going to be doing the talk an algorithm, a quantum query algorithm. So here, what we're trying to state is that if A is a quantum query algorithm that does T queries, then as we have said before, for every X, you're going to have a random variable as the output of your quantum query algorithm. And we take the expectation of that random variable, and that is what is going to be a polynomial of degree at most 2t unbounded.
But the t queries means they apply t times, or just apply a and it return like t answers?
No, the t queries means that the A applies t times the special oracle gate that has the information about the input. So A is going to look like this. It's going to be an alternation of fixed unitaries and the oracle gates, which contain the information about the input. And saying that A does t queries is saying that A uses t times this oracle gate.
Okay, thank you.
Okay. Any more question? Okay, so now, as I was saying, this is a fact. There is no pure converse for the polynomial method, but maybe we can wonder if there is something similar to a converse that is not exactly a pure converse in the mathematical sense. So this was also wondered by Aronson and Baines, Iraitz, Kokainis, and Smortrops in 2015, where they proved that there is a multiplicative converse for polynomials of degree 2. What I mean by this? By this, I mean that there is a positive constant that lies between 0 and 1, such that for every bounded polynomial of degree at most 2, there exists a one-query quantum algorithm that outputs the polynomial times the constant. If this constant was exactly 1, then we would have a pure converse for polynomials of degree 2, but that is not true. We need this multiplicative constant that can be regarded as a multiplicative error to have a converse. So that is why this is not a pure converse, and instead is what we call a multiplicative converse. And a multiplicative error in terms of quantum query complexity is a bit odd, because what we were trying to do, if you remember the definitions of the measures of complexity that we have introduced, there the error was allowed to be additive. We were wondering about the difference between our algorithm and what we wanted to output. So this is not super interesting, having a multiplicative converse. What is more interesting is that this multiplicative converse implies an additive converse. And this is true because if you take the polynomial minus the expectation of the algorithm that outputs c times the polynomial, then that difference in absolute value is going to be upper bounded by 1 minus the constant. And this means that if you have a polynomial of degree at most 2 that is bounded, then you can output that polynomial using just one query quantum algorithm up to some error that you can control and is universal. Okay, so this means that this multiplicative converse implies an additive converse. Also, what I want to say is that the techniques that Aronson and co-authors use in order to prove this result were basically the Grothendieck inequality. And for those who know, the Grothendieck inequality is an inequality that compares the completely bounded norm and the infinity norm of a matrix, which is going to be important. This is the second time that the infinity norm pops out in this talk, and it's going to pop out a bit later too. And in particular, what we can say about this constant, thanks to the proof technique, is that if you restrict yourself to bilinear forms, which are polynomials written as stated in this second bullet of the slide, then the constant can be taken to be 1 over the Grothendieck constant, which is the constant that appears on the comparison of the infinity norm and the CB norm due to the Grothendieck inequality. This implies an additive converse with 1 minus 1 over the Grothendieck constant as an additive error. Okay, so it's going to be keeping this in mind, and I also want to say that we also have a finite dimensional Grothendieck constant, which means that if you restrict your matrix that define the bilinear form to be of certain dimension, let's say 2, if you have that matrix 2 by 2, then the Grothendieck constant can be improved to be the two-dimensional Grothendieck constant using the techniques of Aronson and co-authors. Okay, so Now we have this first idea on how to define a converse for the polynomial method by Aronson and co-authors, and they also wondered if they could extend their ideas to higher degree. As I said, this is not clear using the techniques, because their techniques use the growth inequality, and the growth inequality is something very special of polynomials of degree 2. It's not true for polynomials of degree already 3. So it's not clear how to generalize their techniques to higher degree, and in particular, they wondered if their result about an additive converse was true for polynomials of degree 4 and quantum query algorithms of 2 queries. So that is the question that they wondered about also in the paper, and you can also wonder about the analog question for the multiplicative converse. Is the multiplicative converse true for polynomials of degree 4 and quantum query algorithms of degree 2? And if anyone has a question about this first reflection on the possible converses, please ask it. Okay, if there is no question, I just want to stress that remember that we don't have a pure converse for the polynomial method, so now we can wonder about something that looks like a converse and is not a pure converse. Aronson and co-authors did that for polynomials of degree 2, and they didn't know how to do it already for polynomials of degree 4. They didn't know if there was an additive converse nor a multiplicative converse. And the first of our results is saying that there is no multiplicative converse for polynomials of degree 4. And to prove this, what we do is give a family of polynomials that rule out this possibility. We give, in fact, two families. One family is randomly given. Using the probabilistic method, we can control that family of polynomials and rule out the existence of a converse to the polynomial method using this family. And also, we are going to, we also gave in the paper an explicit example using techniques of additive combinatorics to control the things that we have to control about this example. We are not going to talk about the explicit example in this talk. We are just going to mention it because otherwise we wouldn't have time, I'm afraid. So this the first of our results, and the second of our results is showing that the technique of Aronson and co-authors to turn a binary form into a one-query quantum algorithm is optimal for binary forms that are of 2 by 2 variables. So we are going to show that the best additive error that you can obtain for this kind of binary forms, the best additive error of approximation with one query quantum algorithm is 1 minus 1 over the growth constant of dimension 2, which is what Aronson and co-authors obtained. So the techniques are tight, are perfect, at least for one simple case. And finally, what we are going to show also is that there is no hybrid converse with a small additive error for polynomials of degree 4. Okay, so first of all, now I have to speak about what is a hybrid converse. I have already said what is a multiplicative converse, which is this converse that has a multiplicative error. I have said what is an additive converse, which is the converse with an additive error, and now I'm going to say what is a hybrid converse, which is going to be a converse that has both the multiplicative and the additive error. So far, the first of our results states that it is not true that there is a multiplicative converse. So this logical sentence is not true. It's not true that there exists a constant such that for every bounded polynomial of degree 4, there exists a two-query quantum algorithm that outputs exactly the polynomial times the constant. So if we rearrange, we are saying the same. If we put everything in one side and put absolute value, and what we know is that this is not true, but maybe if we allow in this expression an additive error, this can be true. So maybe there can be a converse that admitting both a multiplicative error and an additive error is true. So maybe there can be a hybrid converse. Okay, so the last of our results is saying that not only this epsilon cannot be 0, which means that there can be no multiplicative converse, but also this epsilon cannot be super small. So What we prove in the last of our results is that there is no hybrid converse with a small additive error. So if there were some C and epsilon such that this statement was true, the epsilon cannot be super small, which is stronger than saying that there is no multiplicative converse for polynomials of degree 4. Okay, so are the results clear? Any question about them?
Yeah, we think it's fine. Thank you.
Okay. Okay, thank you. Let's go. So now we are going to introduce the tool that we are going to use. Okay, so maybe the most important tool for our work, the most differentiating one, was our work of Nuno Chalam, also Job Briet, and Parazuelos of 2017, where they fully characterize how are the output of quantum query algorithms. Remember that by the polynomial method, we know that if a polynomial is the output of a quantum query algorithm, then it's bounded in degree and also bounded in the infinity norm. Well, what Aaron Chalam and co-authors proved in this work is that they can fully characterize the outputs of quantum query algorithms. Namely, what they can do is saying that a polynomial is the output of a quantum query algorithm if and only if it's bounded in degree and also is bounded in the completely bounded norm. We are not going to use something as strong. We are just going to use part of the work, which is less strong because we don't need more. But I just want you to remember that this completely bounded norm has already popped out. Okay, we thanks to this result of Ronald Chalan co-authors, we can fully characterize quantum query algorithms by something that resembles to the polynomial method, but now is with double implication, and now instead of having the infinity norm bounded by 1, you have the completely bounded norm bounded by 1. Okay, so that is something that is going to be nice, because this way you are going to remember that this completely bounded norm and the infinity norm is the same that appears in the Grothendieck degree equality. But what we have to focus now is on this part of their work, where they only say a bit more than the polynomial method did. In particular, what they did is prove that if a polynomial P is the output of a T-query quantum algorithm, then that polynomial is the restriction of a 2T form of one more variable that is bounded in the ICCB norm. I'm going to say now what is everything here, because I have not defined what is a 2T form. A 2T form is simply an homogeneous polynomial of degree 2T. And the ICCB norm is, and the ICCB norm is just another norm that is a bit smaller than the completely bounded norm and is related to it. In particular, you can regard the ICCB norm as the infinity norm, but now instead of evaluating your polynomial in numbers, in real numbers that are bounded by 1, you evaluate it in matrices that are bounded in the operator norm by 1 and also commute. So I think that there is no problem, because if you have that the matrix commute, is completely clear how to evaluate the polynomial in matrices. And this is like the analog of the infinity norm, but now you allow matrices that commute and that have bound in the operator norm. And these matrices are square matrices of any dimension. So somehow the ICCB norm is the same as the infinity norm, but now you allow to take the supremum over matrices. So what this result says is that if a polynomial is the output of the query quantum algorithm, it can be extended to one more variable in a way such that is an homogeneous polynomial of degree 2T and is bounded in this norm, the ICCB norm, that also take into account how big you are in matrices. So now let me explain why this result is stronger than the polynomial method. Well, this result is stronger than the polynomial method because if you evaluate this H in a bit string and the number 1, which in particular these things are matrices that are bounded by 1 and they commute, then thanks to the bound of the ICCB norm, you know that this H evaluated in x, 1 is going to be at most 1, and as P is going to be equal to x restricted to the last variable being 1, then P is going to be bounded by 1 in all the elements of the Boolean hypercube. So this bound on the ICCV norm of H implies the bound on the infinity norm of P. So this result tells you more about how are the outputs of T-query quantum algorithms than the polynomial method did. Okay, is this result clear? Because this is like the most powerful previous word that we're going to use.
Sorry, one point I do not understand. When you mention this apply to infinite dimension, you are talking about the size, the matrix size of A, or are you talking about the number of N?
What I mean is that I take dimension D, I take n plus 1 matrices that are of dimension D times D,
Yes.
and they also commute, and I evaluate the polynomial in that set of matrices. Is that clear how to do it?
But when you mention apply for infinite dimension, you mean D allowed to be infinite, or you?
No. So sorry, I was not precise. Yeah, I was wrong. In fact, it applies for a finite dimension but unbounded dimension. You can take D as big as you want.
D can be as large as you want. And how
Yes.
about the N, the number of N?
N is fixed because H is a polynomial that takes as an input n plus 1 variables.
Okay, it's the degree of the polynomial, so fixed. I see. Thank you.
The degree is 2t, but it takes n plus 2 variables as input. N plus 1, sorry.
Okay, N plus, okay, thank you.
Thank you for the question. Anything else? This thing about the dimension of the matrices not being explicitly written is always an issue. Sorry, I should change that. Okay, if there is no more question, I will continue. And so we have the result that is stronger than the polynomial method, and combining it with two lemmas that we prove in the paper, then we are going to rule out the existence of a multiplicative converse for polynomials of degree 4. First of all, well, remember that here, if you have that P is the output of a T-query quantum algorithm, then you have an upper bound on the ICCV norm of the polynomial. Okay, so now we are going to show in our first lemma that you are also going to have a lower bound for certain extensions of certain degree 4 polynomials. Okay, so in particular, what we do is saying that assume that you have a positive constant C, assume that you have a polynomial of degree 3 that is multilinear, and that you can extend that polynomial times an extra variable times the constant C by an n plus 2 variate form of degree 4 H, then you can have a lower bound for the ICCV norm of the extension in terms of things related to the polynomial that we are going to control in lemma 2. So now again, there are a few new things in this statement. I'm going to explain them now. First of all, we say that P has to be special, P has to be multilinear. And multilinear only means that is free of squares. There can be no terms with a square. There can be no term like x1 squared, x3. There can be a term like x1, x3, x7, but no squares. That means that P is multilinear. Also, this lower bound on the ICCV norm of the extension is done in terms of two things that depend on P. And these two things are the two norm of the coefficients and the delta norm of P. The delta norm is defined in the following way. You can take the coefficients of P and you can regard those elements as a 3 tensor. If you freeze one of the entries of the tensor, you get a matrix. Then you can take the operator norm of the matrix, and you can take the supremum of these all of these operator norms, and then you get the delta norm of P. I don't want you to remember how these things are. I just state them for completeness. But what is important is one thing, that we can lower bound the ICCV norm of the extension using these two things, and the other thing is that we can control how is the quotient of these two things if we choose the multilinear polynomials in a wise way. Okay, and the proof of this dilemma, I'm not going to do it because I think it's maybe too long. It's not super long, but I don't have time for everything, sorry. And I just want to mention that this is essentially a consequence of a construction of Sarantopoulos of more than 50 years ago that allows us to bound the ICCP norm this way by choosing correctly some matrices like this to evaluate the age. So thanks to a construction of Sarantopoulos, we can choose the matrices where we evaluate age wisely and obtain this lower bound. And this lower bound is useful because it is in terms of a quotient of things that we can control. In particular, in the lemma 2, what we do is proving that this quotient of norms, the 2 norm square and the delta norm, can go to infinity. And to do so, what we do is take two approaches, one with a random example and one with an explicit one. We are not going to talk about the explicit one, but we are going to explain the random. And the random one is easy to understand the definition, at least, because it's considered a polynomial of n variables and consider all the multilinear terms of degree 3 that can be created with n variables. And all those terms are going to have coefficients 1 or minus 1 with uniform probability and independently. So you consider all these polynomials that are randomly defined. First, thanks to the Hoeffding bound, you can upper bound the infinity norm of these polynomials with high probability by n squared. On the other hand, if you count the number of monomials that you are going to have, they are going to be n over 3 because there are n over 3 multilinear terms of degree 3. There are only n over 3 ways of choosing 3 elements that are different. And for every of these monomials, the absolute value of the coefficient is going to be 1. So the sum of the squares of the coefficients is going to be n over 3. And as we had that by the Hoeffding bound, the upper bound of the infinity norm of these polynomials is going to be with high probability n squared, then what we get is that the 2 norm squared of these polynomials is going to be something that goes like n over 3 divided by n over 3 divided by n to the power 4, which is what appears here. Then to the power 4 comes because you have to divide 2 times by the infinity norm because after normalizing and squaring, you get n squared squared. So I hope that is clear that this is a lower bound for the 2 norm squared of P, and this was using the Hoeffding bound, which is somehow well known, and using something that is not that well known, but is nothing super special either. We can upper bound the delta norm of the polynomial using some matrix concentration bounds. And that upper bound is by n to the power minus 3 half. So if we put everything together, what we get is that the quotient of these two things goes with n power to 1 half, which goes to infinity when n goes to infinity. So the takeaway message is that with not a very complicated example, we can generate a family of polynomials such that they are multilinear and the quotient of these 2 norms goes to infinity. So the extensions of these things, the extensions to higher to one more variable, are going to be bounded by below in the ICCP norm by something that is big. So this is going to give us a big lower bound, and as we had an constant upper bound thanks to the result of Arnold and co-authors, this is going to lead to a contradiction if we assume that there is a multiplicative converse. So if you want to ask any question about the 2 lemmas that we have just stated, I will be glad to answer, sorry.
thank you. I have two questions. And first is about this lemma, why you are considering the coefficient to be uniform boundary, uniform random variable, which problem setting you are considering to have this polynomial, or you just try to say any coefficient within +1 and -1 is okay for this lemma, or what's the case?
Yeah, okay, sorry. The coefficients are, this is not exactly one polynomial, it's a family of polynomials. And these polynomials are random, which means that the coefficients are not fixed. They take different values, and the values that they can take is -1 and 1 with probability 1/2 each.
Also, this is the family of polynomial you are considering. So they just a set. There is no need to be a random variable for this. Am I correct?
For every n, you define a family of random polynomials.
Yes.
And with high probability, for that n, you are going to be able to choose a polynomial that obtains this quotient of the two norm and the delta norm. So for every n, you define a family of polynomials of which you pick, thanks to the probabilistic method, the correct one. And then for every n, you define this way a polynomial that constitute another sequence or family of polynomials.
So you are sampling from the set defined by each n, and you are trying to bound their probability, the bound.
So just for every n, I have to prove this.
Okay.
And I cannot exactly say, I need the probabilistic method because I don't know exactly which is the one polynomial, which is the correct choice of these things that gives you the bound I'm looking for. But I know that it exists with high probability.
I see. Okay. Okay, thank you. And my another question is about lemma 1.
Yes.
In the delta norm, you are trying to see the soup of this quantity, and are they matrix? I mean, fixed for row for column and row index being ij, and k0 is just some fixed number for this coefficient.
Yes, that's it. You freeze one of the coefficients, the other two are free, so you have a matrix, and then you take the operator of those matrices, you take the supreme one, and that is delta.
Okay, and why there is a 3 index? That they are multilinear of degree 3. Are there any graph correspondings for this setting?
Any graph?
I mean, you also mentioned h, right? Some h. I'm just curious about, is there any problem setting that can correspond to this polynomial?
I don't know, but the reason that we needed multilinearity, it was a bit technical. I mean, it was not clear. In fact, Job Briet, who is my supervisor and the co-author of this paper, also thought about this before, and what they did with the other authors of the original paper about completely bounded polynomials, Arnaud Salam and Palazuelos, what they did was something similar to this, but without considering multilinear polynomials. And you need multilinear polynomials in order to have this statement because of technical reasons. So it's not clear why we need multilinear polynomials. I mean, it's clear for us now because we have done the proof and we have understand why we need it, but it's not easy to explain. It's a bit technical, and it's not something that can be stated with this very few information. So sorry, it's a bit technical, the reason why we need the multilinear polynomials, and there is no intuitive reason, I would say.
Okay, thank you.
Okay, thank you very much for the questions. Any more? Okay, so excuse me?
I'm good.
Okay,
yeah,
thank you. Thank you, perfect. Okay, let's go to the sketch of the proof. So just remember that we have a result that says that if we can extend, we can upper bound the ICB norm of the extension. We have result, which is lemma 1, that says that we can lower bound the ICB norm of the extension. And we have a result that is lemma 2 that says that if you choose well your multilinear polynomials of degree 3, then the extensions of that polynomial times an extra variable times a constant is going to be lower bounded by something that is big. Okay, so now if we put everything together, we can rule out the existence of a multiplicative converse for polynomials of degree 4. Okay, so first of all, use lemma 2 to pick wisely a family of multilinear forms of degree 3 such that they attain a big quotient of these norms that we have talked about. Second, let's assume that the multiplicative converse is true. In other words, there is a positive constant such that for every bounded polynomial of degree at most 4, there is a two-query quantum algorithm. No, sorry, for every bounded polynomial of degree 3, there exists a two-query quantum algorithm that outputs exactly C times an extra variable times the polynomial. So as the polynomial was of degree 3, then this times, if you put the extra variable, is of degree 4. Okay, now thanks to the result of Arunat Salam and co-authors, we know that this implies that there is an extension with one more variable that is bounded by above in the ICB norm. Thanks to our lemma 1, we know that this extension is lower bounded by the quotient of norms of the multilinear form of degree 3. Now, if we put the lower bound and the upper bound together, what we can do is obtain this expression. And if we rearrange the expression, we obtain an upper bound for the constant C. If we take the limit and use the lemma 2, then what we get is that this constant C is upper bounded by 0. And this does not make sense because on the one hand, we assume that C was positive. And now we have reached that C is non-positive. This is a contradiction. And the only thing that we were not sure about was the existence of the multiplicative converse. So this means that the multiplicative converse cannot be true. This way, we rule out the possibility of having a multiplicative converse for the polynomial method for polynomials of degree 4 and quantum algorithms of degree 2. The techniques of Aronson and co-authors for the multiplicative converse do not generalize to higher degree. Is it clear how we have reached this contradiction? Good. Then now we are going to speak briefly about how we moved to our other results. Essentially, we use the same techniques that we have spoken about now, but quantified. And to quantify them, we have to use a semi-definite program given by Girvin and Laurent, also based on the characterization of quantum query algorithms by things that are completely bounded. And these SDPs, if you input a polynomial P and an integer T to it, it outputs the smallest additive error possible when approximating that polynomial with T-query quantum algorithms. Okay, so now if we input the bilinear form defined by the CHSH game and the number 1 to this SDP, we obtain a lower bound that is 1 minus 1 over the rotating constant of dimension 2. And remember that this is also attained by the techniques of Aronson. The techniques of Aronson gives you a quantum query algorithm that approximates a given bilinear form by at most an error of 1 minus 1 over the rotating constant of dimension 2. So this means that the techniques of Aronson and co-authors are tied for 2 by 2 bilinear forms. And I say that this polynomial is the polynomial defined by CHSH game because the polynomial defined by the Heidelberg matrix, which encodes the CHSH game. And this is no surprise. It's no surprise that extremal example for non-local games is also the extreme example here, because as I have said, the Grothendieck inequality was what they used Aronson and co-authors to prove the the multiplicative converse for polynomials of degree 2. And this Grothendieck inequality, as I have said, compares the completely bounded norm of a matrix with the infinity norm. And if you are familiar with the work of Silerson, what he proved was that the completely bounded norm of a matrix is the bias of the corresponding XOR game, and the infinity norm of a matrix is the the completely bounded norm is the quantum bias, and the infinity norm is the classical bias. So we know that when you consider XOR games of two questions, the biggest difference, the biggest quotient between the quantum bias and the classical bias is attained by the CHSH game. So it's no surprise that the extremal example for the XOR games of two questions is the same as the extremal examples for the bilinear forms of 2x2 matrices and one-query quantum algorithms. So with this idea, we used the SDP of Gribner-Laurent to show that the Aronson and co-authors techniques are optimal for 2x2 bilinear matrices. So in a small example, they are optimal. Maybe they are optimal in a broader setting, and that is also one of the results that we have just proved, and I'm going to talk about it in a second. But before, I also want to say that to rule out the hybrid converse, we did something similar to this idea of inputting the CHSH game to the SDP. And now, what we inputted was the family of polynomials that rule out the multiplicative converse. And we inputted that polynomials times the extra variables times C and the number 2 to the SDP, obtaining a lower bound for the additive error that we have to make in order to approximate these polynomials with two-query quantum algorithms. Before, we have only ruled out that this error has to be bigger than 0, and now we give a lower bound to this error. So now we not only show that we have to allow an additive error, but we also give a lower bound for the additive error that we have to allow. So as we were assuming already a multiplicative error, this means that even if you assume both a multiplicative error and an additive error, that additive error cannot be too small. So this means that the hybrid converse cannot be true if the additive error is so small. So there is no hybrid converse with a small additive error, which is stronger than saying that there is no multiplicative converse. Okay, so this is like the end of the proof of our results, of the sketch of the proof. So if you have any questions now, you can ask. And the next slide is just going to be a summary of what we have said so far. Okay, good.
Can you can you explain about why you mentioned quantum bias and classical bias again? Are you going to say quantum bias is for some superposition of these X to be some two variable? I'm not sure what you are talking about, the bias.
Are you familiar with XOR games?
Not so familiar.
Not familiar?
Yeah, not familiar.
Okay, so are you familiar with Bell inequalities?
What inequality?
Bell inequality.
Sorry, say again.
Bell inequality?
Bell inequality. Okay, I see. Yeah, I know.
Okay, so maybe if I phrase it in terms of Bell inequalities is better. So the maximum value that you can attain for a Bell functional using quantum strategies is the ICB norm, is the completely bounded norm of the functional. And the best value that you can obtain using classical strategies is the infinity norm of the functional. And the Grothendieck inequality, and that is what Silerson proved. And the Grothendieck inequality relates the completely bounded norm and the infinity norm. So in some sense, the Grothendieck inequality tells you how bigger can be the quantum value of a Bell functional than the classical value. So the Grothendieck inequality, as Silverson realized, tells you how big can a Bell inequality be. And the biggest Bell inequality, when you consider only 2 by 2 Bell functionals where you only have like 2 observables per player, that biggest Bell inequality in this setting is attained by the CHSH game. And as we were also comparing the completely bounded norm and the infinity norm because of this result of Arunachal and co-authors, when you were talking about quantum Fourier algorithms, then it's natural also to look at this example to show that the results of Aronson and co-authors are tight, are optimal somehow. Maybe this was not super clear, but the idea is that the same norms that appear here, they appear in Bell inequalities.
But
so at the end, the examples from the Bell inequalities should work here.
But I'm curious, what's the relation to this polynomial p x y here? Are you talking about the possible value of this polynomial p, or you are talking about is they related to this polynomial?
Yeah. So as we have already defined the infinity norm of this polynomial, right?
Yes.
And that infinity norm, I tell you that is the best that you can do when playing the CHSH game with classical strategies.
But this polynomial gives you a number. Are they a matrix when you're talking about norms?
Yeah, but you can also see the norm as the norm of the polynomial, as the norm of the matrix is equivalent. And the thing is that if you pick the polynomial, this polynomial is related to the CHSH game. Is this essentially the same thing? And if you take the supremum of this polynomial on the elements of the Boolean per cube, you get the infinity norm of the polynomial, which coincides with the biggest value that you can attain when doing the CHSH protocol with classical resources.
Okay. Thank you.
And you can do the same, but now evaluating the polynomial in matrices somehow and obtain the best thing that you can do with quantum resources.
Okay.
And that is the completely bounded norm, and that is what we know that it should be bounded in order to be a quantum Fourier algorithm. It's a bit more long, but yeah, but the idea is that the norms, the objects that we are studying both in quantum Fourier algorithms are the same as the objects that we are studying in Bell inequalities, thanks to the work of Silverson that realized that for Bell inequalities, and the work of Arunachal, Briet, and Palazuelos that realized that for quantum Fourier algorithms. Sorry if this is not clear. If you want to talk offline or another moment about this, I will be happy.
Okay, thank you.
Thank you. And if there is no more question, we can go to the last slide. So, so far, we have finished the core of the presentation. We have said that the polynomial method is something that is very relevant in quantum query complexity. It has been nice and useful, and we can wonder about some philosophical questions about it. In particular, here we answer a few. The first one is that the multiplicative converse that was true for polynomials of degree 2 is not true for polynomials of degree 4. The second question that we answer is, are the techniques used by Aronson and co-authors to show that there is a multiplicative converse for polynomials of degree 2 tight? And yes, they are optimal for 2 by 2 linear forms. It's just that they are optimal in a small example, but that is saying something about how wise they were, because they, at least in one example, could do the best thing that is possible. And for polynomials of degree 4, we have also ruled out the existence of hybrid converse with a small additive error. So finally, I just want to say that in a forthcoming work with Job Briet also and Sander Griblin, we saw something stronger. First of all, that there is no additive converse for polynomials of degree 4, which is stronger than what we have proved in this work, where we have proved that there is no multiplicative converse. And remember that multiplicative converse implies additive converse. So ruling out the multiplicative converse does not rule out an additive converse. So this result is a bit stronger, and it answers what was posted as a question in the paper of Anderson and co-authors. Also, what we do is not only showing that the Anderson and co-authors result is tight for 2 by 2 bilinear forms, but also for n by n bilinear forms where n can be any integer. And this is nice because this characterizes the Grothendieck constant using one-query quantum algorithms. And this is super nice because the Grothendieck constant is something that worries mathematicians quite a lot. This constant has been unknown since Grothendieck posted is to find its exact value in 1953. We have good bounds, lower and upper bounds, but we don't know exactly the value. And this constant and this Grothendieck inequality appears in so many ways in mathematics. So maybe this way we have opened a path to determine the Grothendieck constant using quantum query algorithms. And this way we maybe can close an open problem that has been open for more than 70 years. So this is all I wanted to say, and I just want to thank you again for your attention, for the invitation to the seminar. I'm very glad to give the seminar here, and if you have any other questions or comments that you want to do and you want to do them privately, you can email me, and I will be happy to talk. Thank you very much.
Thank you, Francisco. Is there any questions in the audience?
I mean, just want to ask, in your proof, there is no like this converse, and is there any implication for the quantum adventure or not? Is it good for quantum adventure or bad for quantum advantage?
No, I wouldn't say that there is a quantum advantage here. No, because we are talking about constant queries. We are not saying that we can be polynomially better. This is more like a mathematical question, but we don't really compare classical versus quantum. We have just spoken about classical to motivate the definition of quantum. But in this work, we don't compare the classical and quantum work. So there is no quantum advantage in this work.
I see. Okay, thank you.
In the work of Siverson, there is quantum advantage because there you can measure how well you can do playing a game or violating a Bell inequality using the same mathematical objects that we use here. But we don't apply these mathematical objects to obtain quantum advantage in Bell inequalities. We apply them just to wonder out something of quantum query algorithms.
Okay, very nice. Thank you.
Thank you.
Francisco? Yeah.
Yes.
Yeah, we as you mentioned, we know that polynomial method could give some lower bound for some computer science problems, such as searching problem, the collision finding problem, or the element distinctness.
Yes.
And if we have the converse of the polynomial theory, is there a scenario that we could apply this converse theory?
Yeah, of course. This converse theory is nice because now, if you had the converse, which you have, if you had, instead of the polynomial being bounded infinity nor being bounded in the completely bounded norm, then you not only have a lower bound, you would have an upper bound. Because if you ensure that the polynomial is a restriction of something that is completely bounded, then you have a quantum query algorithm. So you know that you have at most to use a certain number of queries. So that is the application. If we had the converse, the polynomial method would also give you an upper bound, but it does not give you an upper bound because we have no converse. But with the refined version of the polynomial method given by Anuna Chalam, Briet, and Palazuelos, where you substitute the infinity norm by the completely bounded norm, there you have a converse, so you have a way of proving upper bounds the existence of quantum query algorithms that do well.
Okay, thank you.
Okay.
Okay. Okay. If there is no further question, let's thank Francisco again. Yeah.
Thank you very much.
Thank you very much. Thank you.
Very much.
Thank you. Bye-bye.
Bye-bye.
Okay, bye. Thank you.